Hello everyone. In the Redox chemistry chapter, our today's topic is formal potential. So you have heard about the standard electrode potential, which is denoted as E0, but there is another standard electrode potential which is actually derived from the experimental observations. So the E0 value is actually the theoretical value, but depending upon the type or nature of the medium, the ambience, the effect of precipitation or the effect of complex formation, all these so many parameters take place which is actually unknown to us before conducting the combination of two half cell reactions. So when the half cell reactions are taking place, that moment it is found that the original E0 value is deviating from the theoretical value. Okay, so let us find out what should be the definition of formal potential. It is also known as the conditional potential also. So the definition of formal potential is the standard electrode potential observed experimentally in a half cell. So it is actually the experimental standard potential, okay, which is taking place in a half cell, that deviates from the theoretical value due to so this value actually is not equal to that of the theoretical result or theoretical E0 value. Okay, why does it deviate? It happens due to the effect of some other factors such as protonation. Okay, in the acid medium protonation takes place. Complex formation, if there are some ligands present as the acid radicals, so they can form the complex with the metal cations, or sometimes precipitation, the effect of pH, so many factors are there. So due to this, their original standard electrode potential has some changed value. So this is formal potential. Now let's have a look in the Nernst equation, which has a little modification here. Here you find the E equals to E0 dash, okay, or sometimes it is denoted as EF in the suffix small letter f. So I am writing here as E0 dash. This is the formal potential, okay. So instead of E0 you are writing E0 dash, which is called the formal potential, and at 25 degrees Celsius you have converted this ln into log and put all the values including Faraday and 298 Kelvin. Here the equation converts to 0.0591 by n. N is the number of electrons involved. So if this is the Nernst equation, then the experimental value, how would you obtain the experimental value? Just simply at 1 molar concentration of the oxidant and the reductant. So this is log 1 by 1. Overall it is a 0. So that moment E becomes E0, isn't it? So when the concentration of the oxidant and the reductant becomes equal, that is there 1 molar, that moment the electrode potential, which is obtained from the potentiometer by connecting the half cells, is equal to the formal potential, and this value actually deviates from the original theoretical value. Okay, so let's have some elaboration with examples. So as for example, we have to take here the Ferric Ferrous System, which has the theoretical standard electrode potential plus 0.77 volt. Now let us find what happens in its E0 value when it is taken within an acid medium. If it is perchloric acid, 1 molar perchloric acid, then this value actually decreases by 0.02 volt and it becomes plus 0.77 volt to plus 0.75 volt. In presence of 1 molar hydrochloric acid, it decreases more, it becomes plus 0.70 volt. In presence of 1 molar sulfuric acid, it becomes plus 0.68 volt, and if you take an acid mixture containing half molar phosphoric acid and 1 molar sulfuric acid, then it decreases to its least value plus 0.61 volt. So why does it take place? Now let's have a look at this equation. Oxidant is the ferric ion and the reductant is the ferrous ion, that is Fe3 plus concentration in the numerator and Fe2 plus concentration in the denominator. Now this Fe3 plus has the tendency to form complexes. Both have the tendency to form complexes, but Fe3 plus being more positive, it has more tendency to form complexes with these acid radicals such as chlorate, chloride, sulfate, phosphate and sulfate. These types of acid radicals, they form complexes. So as a result, what happens, the free ferric ion concentration reduces a lot. Okay, so the exact value what you have in the laboratory, the exact amount of ferric or ferrous ion present in the solution, you know one value, but in the free form they are present in different value. So what actually happened, by adding acid, the concentration of ferric ion reduced. So suppose you took 1 mole ferric and 1 mole ferrous, okay, but originally you will find that it is not 1 mole, it is less than 1 mole. So this actually fraction becomes less than 1. Okay, this becomes a fraction. In the numerator the value is less than 1, in the denominator the value should be 1 or greater than the concentration of the oxidant. Okay, so this becomes a fraction which is less than 1. So the log of a fraction is a negative value. So this overall parameters become something negative, and this negative impact is affecting this E0 value. As a result, something is deducted from the original plus 77 volt, and as a result these decreased potentials are obtained. Okay, so this is formal potential. So what is the explanation? The value of E0 decreases as the extent of complexation of ferric ions that increases in the order shown above. That means from the top to bottom, the order of tendency to formation of complex increases. Okay, now this is one example where the formal potential is less than the theoretical value, that the standard electrode potential. Okay, now we are having another example where the formal potential would increase. Okay, so in this example we are taking two half cell reactions. Okay, in the one half cell reaction there is ferricyanide ion which is consuming one electron to produce ferrocyanide ion, and it has the electrode potential, standard electrode potential, theoretical, which is plus 0.36 volt. And the another half cell reaction, there is iodine, it is also consuming one electron to produce two iodide ions, which has the standard electrode potential plus 0.54 volt. So which one is more oxidizing? Definitely this iodine is more oxidizing. So the actually this delta G is more negative, so this forward reaction would take place. As a result, it will compel this system to take place in the backward direction. As a result, what would happen? The ferrocyanide ion would release one electron to produce ferricyanide ion. Okay, so this is the theoretical situation. It is therefore expected that iodine should oxidize ferrocyanide to ferricyanide. In fact, that means in reality what happens? The reverse process takes place when the two half cells are combined, as the ferricyanide oxidizes iodide ions quantitatively in 1 molar acid solutions. Okay, that acid may be hydrochloric acid, sulfuric acid or perchloric acid. So what actually happens is this system becomes the oxidizing system and this system becomes the reducing system. So among this, definitely the ferricyanide ion becomes the oxidant and the iodide ion becomes the reductant. The iodide ion loses one electron, that electron is consumed by this ferricyanide ion and thus it becomes ferrocyanide ion. Okay, so how can that be possible? Definitely the E0 value should be more positive and it crosses the 0.54 volt of this redox potential or the standard electrode potential. So since due to something what is happening here, this value increases and crosses past and becoming more positive than this iodine iodide system, so it can quantitatively reduce the iodide into iodine. It liberates iodine and iodometrically you can make quantitative estimation of the ferricyanide ions. Okay, so here the formal potentials provide explanation for such observed behaviors. So how would you explain these abnormalities? So formal potential can resolve this problem. Resolve these problems. Okay. So in so many systems, these types of abnormalities are observed, which can be resolved from the aspect of formal potential. So formal potential provide explanation for such observed behaviors of many redox systems which cannot be explained by standard potential alone. So what happens here? Let's have a look. In the previous example, in the ferric ferrous system, as I said, the complex ions are formed. Okay, and the ferric ion has the more tendency to form complexes with the negative ligands because it is more positive. Now here you look at the ambience of the ionic atmosphere in the ferricyanide and ferrocyanide systems. The ferricyanide is less negative than the ferrocyanide. Okay, so ferrocyanide is a soft base, that is, it is a stronger base, whereas ferricyanide is a comparatively hard base, so it is a weak base. Okay, and definitely since this is more negative, it is having the more negative ambience in its atmosphere around with the cyanide ligands, so it has the more tendency to get protonated than the ferricyanide ions. Okay, definitely according to the Bronsted-Lowry theory, this is a strong base, so its conjugate acid, that means the H FeCN6 3- would be a weak acid. On the other hand, since this is a weak base, so its conjugate acid, that is the H FeCN6 ion, would be a stronger acid. That means it has the more tendency to release the protons, whereas it has less tendency to release the protons. So let's have a look. As such, in such acid medium, the acidic ions H FeCN6 3- and these are actually the conjugate acids. This is coming from the ferrocyanide. Okay, one ferrocyanide, when getting protonated, it produces H FeCN6 3-, and when one FeCN6 3- gets protonated, it produces H FeCN6 2-. So they are formed, the former being weaker one. So definitely this is a weak acid. That means as such the concentration of the free FeCN6 4- ions in the solution is largely decreased. Why is it is decreasing in large extent? Because it is largely getting protonated due to its strong basic behavior, due to its softness. It is easily getting protonated. Okay, so this ferrocyanide ion actually in reality is being present in the solution in a very low concentration. So the E0 dash for the ferrocyanide system increases. It becomes plus 0.71 volt, that is it can now oxidize because it is now more than plus 0.54 volt. So it can easily oxidize iodide ions into iodines. That means it can liberate iodine. Now if you have a glance to the Nernst equation in the previous slide, I move on to the previous slide here. Here is the previous slide. Look, this is the Nernst equation. Now who is the oxidant and who is the reductant? Actually the more oxidation state, the higher oxidation state of iron is ferricyanide. So this is the oxidant. Okay, this is coming from the ferric ion, and the reductant coming from the ferrous ion is the FeCN6 4-, that is the ferrocyanide ion. Now as I have said, the concentration of the reductant, that is the ferrocyanide ion, is decreasing to a large extent. That means this parameter becomes greater than 1. So it is a positive parameter by if you take the logarithm of some number which is greater than 1 and something is added to this E0 value. So it is very much clear that now in this case where the protonation of the ions taking place, the E0 value is increasing. In the previous example, what we found? We found that E0 value was decreasing, but here the E0 value is increasing. Okay, so we have to just theoretically, we have just theoretically explained this phenomenon. Now we can prove this mathematically also. So let's take the help of the Bronsted-Lowry acid-base theory. So according to this theory, the conjugate base of a strong acid is a weak conjugate acid. Okay, the conjugate acid of a weak base is a strong acid, and vice versa. So according to this theory, the FeCN6 4- is a stronger base. As I have said, this is a strong base. Being a soft base, it has the higher tendency to get protonated than the FeCN6 3- ion. And in the acid medium, both ferrocyanide and ferricyanide, or that means both the ions, FeCN6 4-, FeCN6 3-, both of them get protonated to form acidic ions. That is, their conjugated acids are formed. So the conjugated acids are HFeCN6 3- and HFeCN6 2-. This is coming from the ferrocyanide ion, and this is coming from the ferricyanide ion. Hence, according to the Bronsted-Lowry theory, HFeCN6 3- is a weak acid because it is the conjugate acid of a strong base, which is the ferrocyanide. So it's the acidic form should be a weaker one. As a result, or in comparison to the previous one, this one should be comparatively a stronger acid. Which one? The HFeCN6 2-. Okay. Now let us express the tendency to get ionized mathematically in terms of K1 and K2. K1 and K2 means acid dissociation constant. So the protonation reactions are here: ferrocyanide getting protonated, this one is produced, and ferricyanide getting protonated, this species is produced. So the what should be the, what about the K1 and K2 values? Just according to this active mass formula, the products in the numerator and the reactant concentrations in the denominator. So thus we get equation A and B. Okay. Now we know that K1 is very much greater than K2. Why K1 is greater than K2? Because this is a very weak acid, comparatively weak acid. Okay. So if this is very weak acid, so it does not decompose. So the numerator in this parameter is very large. So the K1 value should be very high than this K2 value. Okay. And if you rearrange equation A and B, then we get equation C and D. Okay. Now among the ferrocyanide and ferricyanide ions present in the solution, some are present as the free ions. That means some are getting protonated and some remaining unprotonated. That means they are present both as free ions and protonated forms. Therefore, their total concentrations may be calculated as follows. So we have to count them, their total concentration. So what is their total concentration? This is the ferrocyanide total. This suffix T means total, and this is the concentration of ferricyanide total. Okay, total means that this is the unprotonated form and this is the protonated form. In case of ferricyanide also, this is the protonated for unprotonated form and this is the protonated form. Okay, so these are the total count of their concentration. Now we have obtained the values of the protonated forms from the equation C and D. Okay, in the equation C and D, and these values when we put here in the above two equations, we get these two equations. Instead of HFeCN6 3- concentration, we are putting the right hand side value from equation C and this right hand side from the equation D. Okay, in terms of K1 and K2. Now take in common the K4 FeCN6 4-. Then after having taken the common, you get these parameters in the embraces. So thus we get equation E and F, and finally thus we can get the exact concentrations of the oxidant, that means the ferricyanide ion, and the reductants, that is the ferrocyanide ion, in terms of their total concentrations. So what we know actually, what we have put in the solution. Okay, and that is actually the total concentration. So this total concentration can now be calculated as this one. In terms of total concentration, their their concentration, the free ion concentration, can be expressed this way. So this is the free concentration of FeCN6 4- in terms of total concentration of FeCN6 4- and free concentration of FeCN6 3- in terms of total concentration of FeCN6 3- and also in terms of K1 and K2. The Nernst equation at 25 degrees Celsius. What is the equation? This is the equation. Just I have put here E0, not E0 dash. This is the theoretical equation. Okay. Now this is, since there are one electron involved, so we have to put n equal to 1. Okay. And in case in the place of oxidant, the ferricyanide as usual, and in place of reductant, the ferrocyanide as usual. Now this concentration of ferrocyanide and ferrocyanide concentrations are replaced by this right hand side of these two equations. Okay, so these two we have got. Now we have to rearrange this equation or separate these K1 K2 values in another term. Thus you get, look, the K1 K2 parts have been separated and the original concentrations of the FeCN6 minus and FeCN6 minus have been placed here. Okay, so this is the part actually which is getting added to the theoretical E0 value. Okay, so this theoretical value of E0 is increasing and this is actually the E0 dash value, which is called the formal potential. If you take a 1 molar acidic solution and put H plus concentration as 1, then you will find that this parameter is at 25 degrees 0.35 volt. Okay, since K1 is very much greater than K2, so something is to be added here. Log parameter is producing some positive value, and so something is added with this, and thus the E0 value, E0 dash value is originally 0.36, the E0 value plus the added value 0.35, that means it becomes 0.71 volt. So it is now crossing past the value of iodine iodide system, which is actually plus 0.54. So it is playing the role of an oxidant, and in turn the iodide becomes the reductant. As a result, ferrocyanide can oxidize iodide into to liberate iodine, and they can be estimated quantitatively. So that's all about formal potential. Okay, so thank you very much, take care, goodbye.